This presentation is going to be about how to improve exploration in reinforcement learning, and it's going to be on two main shortcomings that we currently have in some exploration methods for RL and how to overcome those limitations. So fortunately, coming after John, I don't have to speak much about reinforcement learning and the exploration problem to some extent. So this is going to help me in shortening the intro part of the talk. So just to recall basically what reinforcement learning is about learning how to maximize a long-term reward. So here I'm talking about what John referred to as multi-step reinforcement learning. And so we have an agent which interacts with the environment, and every time we observe a state, we take an action, we receive a reward, and we drive the change in the state. So the difference between contextual bandit and RL is that here we are responsible for changing the state of the environment, and so we can even influence the next observation somehow. And overall, the objective is by interacting with this environment, we would like to find how to take actions in such a way that we can accumulate as much reward as possible over time. John even mentioned the recent successes of reinforcement learning, for instance, in Atari and in Go. And one of the amazing things is that by using these simulated environments in Atari and simulated Go in the sense that they are playing against the same agent over and over in the attempt to optimize performance, we achieved in the recent years, I mean reinforcement learning community, so these results are by DeepMind, results which are very impressive, at least for the time. We didn't even expect that reinforcement learning could perform so well in these games. And here, for instance, Atari achieved, and these results have actually been improved over time, above human performance. And here, AlphaGo 0, been able to improve a lot the performance and reaching a world champion level, and now even much farther than that. So given this, we could say, okay, reinforcement learning works, so why don't we go beyond games and solve, let's say, real-world problems, which can be recommendation, education, human-computer or human-robot interaction. So one of the issues is that when we just go beyond the performance and we look at the learning performance, so the actual training phase, we notice that in both cases, both in case of Atari and Go, the time to reach that performance is really, really long. In the case of Atari, we are talking about millions of frames, millions of games. And in the case of Go, we are talking about 5 million simulated games before reaching satisfactory performance. So the bad news somehow is that RL most successful algorithms are sample inefficient in the sense that they really need a lot of samples before getting to a decent performance. And somehow one reason is that we do not explore efficiently the environment. And this means that in order to make these algorithms better, we need to understand how to effectively explore an unknown environment and learn an approximately optimal policy. The potential implications of better exploration are towards a lot of the settings that John described, like recommendation, robotics, human-computer interaction, and so on and so forth, which are intrinsically problems where we don't have access to a simulator that we can spend ages interacting with. We have very expensive samples, and so from each sample we have to get the best and being able somehow to learn fast according to the limited exploration that we have. So over this talk, what I'm going to do is to cover the optimism phase of in uncertainty principle, which already John covered to some extent with the confidence regressor. And I will mention two of the limitations of this approach in reinforcement learning, and then I will draw some conclusions. So the standard model that we have to describe a reinforcement learning task is the Markov decision process. And here I'm introducing basically the state space, the set of states, the actions that the agent can perform. And again, one of the key ingredients is the fact that whenever we perform an action, not only we obtain a reward, which is related to the quality of that action, but we also drive somehow the change in the environment state. And overall, the objective is to create a policy, so a mapping between states to actions, in such a way that we can collect a lot of reward. Now, this a lot of reward needs to be defined a little bit better. And specifically in here, I will consider the case for finite state action space to be able to derive theoretical guarantees. And the objective that we are focusing on is, in this presentation, is maximizing the average asymptotic reward. So let me just browse over this equation here. We will say that the quality of a policy pi once executed in an MDPM is the average reward that we obtain over time when the time tends to infinity. So it's a sort of stationary behavior of the policy over the long period. And the objective is to find the policy pi star that maximizes this quantity in the MDPM. And I will also use G star to denote the largest amount of reward that any policy can obtain. So now we have defined basically how we score a policy. And we would like to understand how we can actually learn through direct exploration of the environment, how we can learn and approximate this policy as quickly as possible. So let me illustrate a little bit more all these elements in this very simple and basic example. Imagine that I'm the agent that needs to navigate over this terrain. And these are the states that are possible, so all possible positions over the terrain. The actions that we can take are just left and right, so we keep it very simple. And we have some rewards, which can be either positive, like this pot of gold, or negative, like this paddle. So going through a paddle is a negative reward. And we have the dynamics, which is, okay, when I take an action in a given state, for instance, if I'm at the top of the mountain and I go left, I will drop a lot. On the other hand, if I want to go up to the mountain, it might be more difficult to go up. And what we would like to find is the optimal policy, which in this case is going towards the largest possible reward that I can get over this environment. The learning problem is to just interact with the system. We observe a state, we take an action, we observe the next state and the reward associated. We have a long trajectory of this kind of interaction, and we would like, as time goes on, to collect rewards which are better and better over time. So the learning problem starts like this. Basically, I don't know anything. So here I put some clouds that say I know just the states that are available, but I know nothing about the rewards, and I know nothing about how the environment behaves. And somewhere there is a true environment which I'm interacting with, but I know nothing about that. So I take a few actions, and I partially reveal, I hope that it's kind of can be seen even from the back, that I start revealing a little bit about the environment, its dynamics, and its reward. So the first step that we do is to just estimate, given this information that we have, how the environment seems to be working. Seems to be working because I'm relying just on some random samples, which are a partial information about how the true environment is behaving. So what I'm going to do at this point, and again, I stress that here we are in finite state and actions, all I'm doing is really just to take the average rewards that I observed. So for instance, this quantity R hat is the average rewards that I observed over time whenever I was in state S and I took the action A. And this part in here, on the other hand, is the estimated transition probability whenever I was in a state S and I performed an action A. This is, according to the samples I observed so far, is my estimate of the probability to transition to S prime. These objects here are just the corresponding counters, so I'm doing really just frequency estimation. So what can this environment look like? It's something as bad as this, and because at the beginning I know relatively little about the true environment. I just relied on a few samples. And you see that there is quite a huge difference between the estimated environment and the true environment. Particular, for instance, here I have that I didn't really capture exactly the fact that there was a very, very tall mountain in here. And so whenever I will be trying to go there, the dynamics that I will discover is different from the one that I estimated. And similarly for the rewards, maybe I was very lucky when I passed by this state, I observed very good reward. And so I estimate that there will always be a large reward in this area, but this is not true because I actually relied, again, on very few estimates, very few samples to construct my estimates. So I have to somehow also be aware that relying on just this estimated environment to decide what to do next might be very bad. So this is somehow what the greedy approach would do. I just rely on samples, I estimate something, and then I perform the optimal policy according to this estimation. So this, as you can see in here, might be very unreliable. And additionally, even if I put some epsilon greedy exploration strategy, it might be very, very inefficient. Like eventually I might actually discover what is the true environment, but it might take forever. So now I have to introduce a second ingredient, which is an estimation of how uncertain I am about my estimates. So are these estimates just totally random guess because I passed there just once and I have very little information about that? Or they're more accurate guesses because I have observed that part of the state space a lot, and so I have more information about that. So this is translated in a more formal way by creating confidence intervals. It's exactly the same idea that John described, where we have different actions, and here we also have states, and we estimate both the reward and the transition probabilities, but we also construct some confidence intervals around them. So we observe so far an estimated reward ahead, but we are very uncertain, and so we know that the true reward might be more or less close to our head by a quantity, which here I'm not entering into the formal details about how to define it, but it's some sort of high probability confidence interval that we put here. So what we are effectively doing is just saying, we observe so far something that looks like this estimated environment, but we're also aware that this estimation might be very inaccurate. And the result of this being aware of the uncertainty leads to this space of possible or plausible environments which look like the estimated one up to some confidence intervals. So this set here that I call plausible environments is all the things that, given the uncertainty that I have, might actually be the true environment according to what I observed so far. So let's go again to the example. It means that, yeah, I have some estimated environment, but from what I know, all of these environments are also possible, maybe more or less likely, but given what I know, little I know about the environment, there might be, the true environment might look like this, or it might be very simple. You see that this is very flat with a lot of good rewards, or it might be very difficult. And I'm taking into consideration basically all the uncertainty that I have in order to create this list of possible, plausible environments. So now I have to decide what to do next, right? So I estimated the environment. I'm self-aware somehow of the uncertainty that I have about that. What should I do next? And one approach, one of different possible approaches, is to be optimistic. So formally, this means the following. I will use this curly MT to denote the set of plausible environments. If you remember at the beginning, I said, okay, what we want is, given an MDP, to find the policy which maximizes its performance. But now I don't know which MDP to use. If I wanted to be greedy, here I would put just M hat, the estimated environment. Here I want to be optimistic. So I first construct the list of plausible environments, and I take the one which is the most favorable, in the sense that under the optimal policy is the one which will have the largest possible reward. And this pair here will be the pair of optimistic MDP, this M tilde, and optimistic policy associated to it. So again, it's an extension to what, if you're familiar with Bandit, UCB kind of approach, is an extension of that idea to Markov decision processes and reinforcement learning. And notice that now I will discuss later how to solve this problem, but the interesting part is that it's more and more used as an approach even in deep reinforcement learning to try to have more efficient exploration. So this is just a way to justify why somehow we should care about this type of approaches, because it seems like in practice, not just from a theoretical point of view, they're effective in driving useful exploration and in increasing sample efficiency in RL algorithms. Okay, so now we have an idea about what to do with what we know and what we don't know, the uncertainty that we have. And in here, what it means to be optimistic? Well, it means to take among the plausible environments the one which has the largest rewards, so you see that these gold pots are very big, and this paddle, which was a negative reward, I estimated as small as I can. And also the dynamics, I will try to find the shape of the environment which is the most favorable. So instead of creating environments where it's very difficult to navigate because of the mountains, I will try to pick the one which is the easiest to navigate over. And so in this case, it's the one which is very flat, so that the access to these very big rewards is very easy. I compute so I select the optimistic environment. I compute the optimal policy in this imagined optimistic environment. And in this case, it will be, well, just try to navigate this way and target the biggest reward that I can. The problem is that I'm not acting in this environment. I'm actually acting in the one above. But the idea is that this way, if I'm right, in the sense this is indeed the true environment, I will gain a lot of reward because I'm acting optimally according to it. On the other hand, if I'm wrong, well, I will explore more and I will gather more information, and later on I will have better estimates, more refined plausible environments, and so I will have learned something useful later. So the idea is that this is what I actually observed so far. I execute that policy that I believe being optimal. Turns out not to be the right one, but at least now I gather more information about a part of the environment which I knew very poorly somehow. So the idea is that at this point, the originally estimated environment is improved, so I get a better information about what happens in this part of the state space, and I repeat the game. I create the uncertainty that I have about that, which now will be much lower in this part, and it will be still a little bit higher in this part. I create the most optimistic, plausible environment, and I keep going. And so this way, I kind of trade off between exploration and exploitation in the sense that the optimal policy that I computed, what the optimistic one, was good if the true environment was indeed the optimistic one. So I was doing effective exploitation to some extent. But if it was not true, so it was a wrong guess, the one I made, well, at least I'm exploring effectively the environment. So I'm at the same time, in some sense, exploiting the information that I gathered so far, but also exploring effectively the environment. So how do we judge whether an algorithm is good or not in doing this game? One of the possibilities is to use the definition of regret, and it's very intuitive. So imagine that I plot a typical learning curve. So I have amount of samples, and this is the reward that I get at each step. We know that somewhere there is the optimal policy, which would always gather the largest possible reward. What we know is that the steeper this curve, the better, right? So that's the intuition of all learning speed of a learning algorithm. So the way that we define the quality is basically by measuring the area between the two curves, well, this line and the learning curve. And this is the amount of reward that if I knew the true optimal policy is I would have obtained, and what I obtained because I didn't know about that. So this is the reason why it's usually called regret. It's regret of not knowing something. And it's basically, if this area is very large, the regret is large, and I'm not doing a very good exploration. On the other hand, if this area is small, then it means I'm very happy because I'm approaching the optimal performance very quickly. Okay, so what is what do we know about this optimistic approach to reinforcement learning? That it kind of works in this sense. So in the sense that the regret is at most as large as this one. So let me just browse over this equation here. So n is the number of samples that I obtain. And we want that area to be as small as possible. So we would like to say that this regret here is smaller than a certain quantity. So this quantity here shows that we grow as square root of n. So the more the samples, the bigger the regret. But this might be a little bit surprising, but consider that whenever I add a little bit of sample, the area can all increase. Right, so we cannot expect somehow the regret to start decreasing at a certain point because it's a cumulative quantity. So it's kind of intuitive, the fact that it keeps growing. Here, the bad news somehow is that we have a linear dependency on the number of states. So we know that the reinforcement learning, the more states we have, the more difficult it's going to be. But this, to some extent, we can expect it, right? We have to learn more things the more states we have. The bad news is actually this D here, which I will define in a moment, which is the diameter of the MDP. So let me dig a little bit more into this and why it's a kind of non-full intuitive limitation of this approach. So the diameter is, I will use the example in here. Imagine that I take this state here on the left farmost and the rightmost corner of this state space. Basically, the diameter is measuring how long does it take to go from here to here. So it's really just measuring the size, if you want, of the MDP. Not in terms of states or actions, but in terms really of time it takes to go and gather information. If I was here, how long does it take to gather information when I'm here? Well, it takes some time, and I will have to pay for it. So this has some intuition behind it, but at the same time, it means that, for instance, if I have a taller mountain here, then the problem becomes even more difficult. And if I add other mountains, then it becomes even more and more difficult. But if you recall the optimal policy was to go in this area here. There was a big reward in the original example. And I might not really care that much about the fact that it takes a long time to go from here to here. The fact that it takes a lot of steps, it does not really necessarily correspond to a bad regret, intuitively. Because again, maybe I don't even care about going here, or maybe going here is actually the optimal policy, and so I don't even suffer any regret by doing that. So although this size of the MDP makes some sense, we feel a little bit like it's over pessimistic in the way we should expect our reinforcement learning algorithms to work. And it's an open question to some extent whether this can be improved, and I will show you one case where it can be. The second type of limitation is even more practical in some sense. In reinforcement learning, we always start with, we have a Markov decision process, which is defined on a set of states. And as soon as we start from there, we say, okay, that's the definition of where the agent can be. Turns out that in practice, I can define a set of states which might not actually be reachable from by the agent at any point in time. And just because it's practical, imagine that I have a state which is defined over, I don't know, a navigation problem, which is X and Y in this room, for instance. So it's very convenient to define the state space as all possible coordinates in this room, except for the fact that there are columns and there are states, so specific configurations of points X and Y, which are not reachable. But from the learning agent point of view, as soon as the learning agent receives as input these states, it assumes by definition that these are things that potentially are useful to reach. And if I have an optimistic approach, and here basically in the picture means that I define the states also in this area which actually don't exist, they cannot be reached. An optimistic approach would say, oh, I don't know much about what happens when I'm in the column. So let's try to go there. Let's put a big reward and try to see what happens. And so I will try to enter into the column. And you can understand it's not a very smart algorithm trying to do that, because I would keep trying to do things which are not actually possible. And the attempt of exploring things which are not possible translates into a very, very, very poor performance overall. I notice that, again, this is very common in practice in the sense that when I define the state space, I don't know in advance which parts of the state space are reachable or not. I just define it as the global constraints that somehow my variable can have, but this doesn't mean that I know in advance perfectly all and only the states that are reachable. So usually what I do is to define more than those that are reachable, just to be sure somehow. Okay, so basically the second part now is going to be about trying to define what are the ways to approach these two limitations. One was the one of the diameter, and the other one is about states which are misspecified in the sense that are provided as input to the algorithm, but they're not actually reachable. So the first one is bias pants constraint exploration, and it relies on some prior knowledge. And I will try to explain what is the form of prior knowledge that we require for this algorithm. In order to do that, I have to introduce another function. So far I defined the performance of a policy in a specific NDP. So this GPI was the average reward that I could get. And this quantity here says, okay, start from state S, and compare the amount of reward that you can get starting from S and the amount of reward that you can get on average asymptotically, so which is the definition of this G function. So this somehow measures the difference between the actual reward that I can get step by step, starting from S, and the one that I will be able to gain asymptotically over time. Again, I rely on the example to explain it. Imagine that the optimal policy, if here I just have this big reward and this is a negative reward, and I accumulate a negative reward of -1 every step I do, except for when I pass through the puddle, which has a reward of -3, let's say. So if I start from here, and it takes 5 steps to reach this pot of gold, and then I will be happy to stay here forever in some sense. So if I stay here forever, let's say that I accumulate a reward of 0 just to make it a baseline somehow. In order to get there, I need, under the optimal policy, I need 5 steps, which means that the difference between the reward that I could get if I started from here and the reward that I actually obtained starting from here, they differ by these 5 units of reward. Another example, if I start on the opposite side, this is a much less favorable state because it takes -36 is the number of steps because each step costs 1, -3 because I also have to pass through the puddle, at least for 1 step. So there is this function which measures, again, the difference in potential reward that I can obtain from starting from a given state and starting from the best state or from the stationary distribution of the policy itself. And so I can say that now if I want to compare this state to this state, they have a difference in value, which is the difference between this -5 and the -39 that I can get here. So I can say that in some sense this is a more favorable state than this one when I execute the optimal policy. So we will define this as a sort of difference in potential between 2 different states. And the assumption that we are going to make is that we have some prior knowledge about the largest possible difference between any 2 states. So somehow he's saying, I know that, yeah, sure, there is a difference between states. There are some that are more favorable than others. But the largest possible difference that I can get in terms of rewards is at most this C. So I will say that it's a constant C. So if you want, you see that it's kind of similar to the diameter. The diameter was the amount of time it takes to go from one state to the other. Here I'm not just counting the number of steps, I'm counting the actual reward that I obtained by doing those paths, according to a specific policy, which is the optimal one. So this quantity, again, it says that I know that depending on the state that I start from, things cannot be completely different in terms of cumulative reward that I can obtain. There is at most a difference of C. And I will show that this somehow is a prior knowledge which can be very useful to dramatically reduce the regret that you can get. Well, let's go for now, we have this prior knowledge, so what we want to do is just to plug it into the previous algorithm that we had. So previous algorithm was trying to be optimistic according to the plausible environments. Here we just add the fact that this, sorry, I didn't mention it, so this difference here, I will call it span, the range of this function. We assume that this is bounded by C. And C, again, it's a prior knowledge that we have. So we have now just yet another optimization problem. Let's go for it and see what happens. And the constraint basically is saying, well, you know what? Among all these possible MDPs, I will only consider policies and MDPs which are reasonable, in which I cannot create differences in potential which are bigger than C. Unfortunately, this is a very non-trivial optimization problem. So although the first one without constraint is kind of manageable, whenever we introduce this one, as it is written, it seems considerably more difficult. And so basically the contribution in here was actually to show that there is an algorithm which is able to solve this problem. And it turns out that the algorithm is very trivial, actually. But it works under very, very narrow conditions that luckily for us are verified in our setting. But let's start with how do we solve MDPs? So something as basic as this. So in order to solve an MDP, the basic approach that we can use is to use value iteration. So value iteration is an iterative scheme. It's an iterative algorithm, which says I start with the function initialized at 0, and then I update this function at each iteration using this equation, which is basically an application of the Bellman equation, the optimal Bellman equation. And whenever we stop, so there are specific stopping criterion to manage that, we will return a policy, which is our objective. And we know that if this n tends to infinity, this policy tends to this pi star. So we know that normally we know how to solve an NDP. So it's relatively efficient, its complexity is quadratic in the number of states, is linear in the number of actions. There are actually improved algorithms that can be even just linear in the number of states. So there are ways to manage this scheme in an efficient way. Now what we want to solve is this guy here. And I didn't put here the maximum over the models because somehow the reasonable question is, okay, give me first an environment and let's try to see whether I can solve at least the constraint one single MDP problem. And it's very tempting to say, okay, I just apply the very same algorithm, so I do value iteration, but since I want this function here, this constraint to be respected, I just enforce the constraint at each step. So at each iteration, what I do is to truncate the candidate next function by basically clipping its range. So I will keep the function equal for all the states, except for those that pass somehow the constraint. So what I'm doing is to take a constraint optimization problem. I know that the unconstrained can be solved in an incremental way. And what I do is just an incremental constraint algorithm. So it sounds very kind of simple as an idea. And unfortunately, it doesn't work. So this algorithm here, in general, does not converge. And even when it converges, it might not even give you the right policy as an output. So in general, this seems to be doomed to fail. And again, once we cannot rely on this iterative algorithm, then it seems very tricky to approach this in our problem because it might actually end up to the need of enumerating all possible policies, or even worse, enumerating all possible plausible MDPs. So this seems like it's a very bad news. Fortunately for us, it turns out that it's not as bad as it looks like, in the sense that if we look back at our problem, here we have this maximum over plausible MDPs. So there is in here I will not enter into the actual details. If you remember, the plausible MDPs were MDPs whose reward and transition model were kind of close to the estimated one. Now we take that as a starting point and we work on it. What it means is that we extend actually partially this confidence interval, and we actually introduce a bias which we'll let decrease to 0 as time goes by. We actually bias our estimates of the transition probabilities in order to ensure convergence. So I will not again enter into the details of this couple of tricks, but it turns out that they are sufficient to make the previous algorithm both convergent and convergent to the optimal solution. So the result is that basically now we have this one where I modified, so I perturbed a little bit the set of plausible MDPs. I can go back to a value iteration scheme in an optimistic way, because here you see that I also take the maximum over transition probabilities here and rewards here. And I apply my truncation as suggested by my constraint. So it turns out that this algorithm, again, you can prove that it converges. So we have a result which says that it converges, and it returns a policy which satisfies the constraint. And in some sense, up to that little bias that we introduce, is still optimal. So it's really solving the original optimization problem that we wanted to solve. And this is very good news, because then it means that we can integrate it into our exploration-exploitation algorithm, into the learning part. And what we obtained, so this algorithm I will call is span-constrained learning. I will denote it by SCAL. We replaced that diameter there by the constraint that we impose, which we assume to be an upper bound on the true range of the value functions. So far, it's just a change in the ladder from D to C, so it doesn't seem that important, except for the fact that when we move to, let's say, practice, and by practice I mean something very, very toyish, is a simple navigation problem where we have an agent which has to go to a shop, actually go and mine some gold, to have some money, go to the shop, buy a shield to pass through the dragon, and so on and so forth. So it's a sort of complex navigation problem that we have here. If we look at the two numbers that denote the diameter in this case and the range of the value functions, you see that there is kind of 2 orders of magnitude between these two numbers, roughly. Which means that if I have an algorithm which scales with the diameter, I will have much worse performance than an algorithm which is able, given prior knowledge, to scale with that quantity. And this turns out to be the case. So UCRL is the first algorithm, the one which performs optimistically. And this is the cumulative regret. Again, we expect that as time goes by, these curves should only increase because it's the cumulative regret. So here, the lower, the better. And if we introduce our algorithm with a loose prior knowledge, so this 10 is still bigger than the true exact span of the true optimal policy, we obtain better and better performance as we get closer to the true thing. What happens if my prior knowledge is wrong? So I pass to my algorithm a parameter which is not an upper bound. Then from a theoretical point of view, we don't really know. I mean, in principle, can have as large as unbounded regret, so just keep growing. The good thing is that it turns out that in practice here, I don't have the chart. It still seems to be robust to that and still performs well. Okay, let me just browse relatively quickly. Actually, the idea is relatively simple to the case of misspecified states, and then I will draw very quick conclusions. So here now we want to go to the case where we have no assumption about whether the states are actually reachable or not, and we have not even that assumption about the range of the value function. So what happens in Optimism? So what I said is that, okay, we have these 4 states, and let's say that this guy here is the state that maybe is reachable, maybe not. So far, I observed that from here, I can go to these states. So these are connected, I know it. But this guy, I don't know whether it exists or not. So Optimism says, well, let's try to go there and maybe discover something which is better than what I know so far. So if this state here exists and is good, it's very good. If it doesn't exist, as I said, it's very bad news. This thing can be arbitrarily bad. Let's be greedy on the other sense. We say, okay, you know what? So far, I haven't observed this, so let's pretend that it doesn't exist, even if somebody told me that belongs to the state space. In this case, I can, of course, learn a very good policy over these 3 states, but I might miss a very good reward because maybe that state is just difficult to reach, but it's very rewarding. And so I should actually try to get there. So if S bar does exist, then we suffer again linear regret because we will never be able to learn the optimal policy. So what we do is actually, again, a very simple idea. So imagine that we focus on this state. The largest plausible transition probability to this guy, according to what we observed so far, is this much. So it's the empirical one plus the uncertainty that I have. What we do is very simple idea is let's threshold it. So if this very optimistic probability to reach this guy is low, then we just truncate it to 0. So it's really a truncation that we do. And we say that this state here is not reachable. On the other hand, if this largest plausible probability to get there is high enough, then let's keep it enabled as a state, and let's try to go there. So here we set a threshold which decreases over time and try somehow to capture this idea of let's try to go there, but not really, right? So if seems like I can go there by enough, then let's try. If it's not by enough, let's discard it. And somehow this is the idea behind, again, we are modifying the set of plausible MDPs by truncating their transition probabilities to 0 whenever there is not enough evidence that I could actually go there. So this simple algorithm, without any prior knowledge about the true environment, satisfies this regret bound. So you see that we go back to the diameter. This is bad news. But again, we have no prior knowledge at this point. So it's probably something that we cannot avoid. The difference is that now this is not the diameter of the true MDP, because the true MDP, if there are states which are not reachable, the diameter is infinite in the sense that it takes forever to get to an unreachable state. This here is just the diameter of the communicating part, so the part that I can actually reach starting from the initial state that I have. So again, an example, this is a kind of famous navigation problem in reinforcement learning is the taxi navigation problem. We have a little car that needs to navigate through the environment and pick up a passenger and put it down. It turns out that if you define the state space in a very natural way, there are 500 states, but only 400 of them are actually reachable. So what happens if you run an optimistic algorithm is that the cumulative regret just keeps growing and growing and growing in an unbounded fashion. On the other hand, the algorithm that we have is able to learn actually which states are reachable and learn a good policy near to the optimal one as the time progresses. And this one, on the other hand, again, the dashed one is if I have prior knowledge, then I could do even much, much better than this one. But this one is, you give me a set of states, are ill-defined, and I try my best to guess whether those states are actually true or not. Okay, so basically these are two ways of address some of the limitations that we currently have in reinforcement learning when we perform exploration. And I just want to spend 1 second on this part, which is, okay, now that we have these beautiful theorems, can we actually do something which is more practical? And the answer is, well, so. So it's very complicated to port these algorithms into, let's say, continuous state actions problems. And one of the reasons is that value iteration algorithm is very difficult to generalize beyond finite state action spaces or very structured MDP. So if you estimate your model with a neural network, what should we do with that? How do we plan with that? It's a kind of relatively open problem, and it's a very difficult thing. But at least the hope is that the lessons that we learn in here are going to be useful to design more robust and better performing exploration strategies once we integrate them with the power of deep reinforcement learning algorithms. Okay, thank you very much.
So we do have time for a few questions, yeah?
Hello, thank you for your talk. Do you have an idea or an intuition on the relationship between the span and the diameter?
Yeah, so in general, there's no relationship in the sense that, in the worst case, the diameter can be equal to the span. So I should say the other way around, in the sense that if I design a very, very nasty reward function, I can make the span as large as the diameter and not bigger. So the span is always smaller than the diameter. The thing is that the diameter can be infinitely bigger than the span. The case of unreachable states is kind of hinting to that, where the span can be still relatively small, but the diameter can be almost infinite. So we have the diameter is an upper bound on the span, and the gap can be arbitrarily large, although we can define reward functions where the two matches.
Thanks. Just one question. Is there any reason why you're using the total variation distance to define the plausible MDPs? Because the meta algorithm is going to invariably depend on what sort of geometry you have on this script M, on how you measure closeness in the MDP models.
Yeah, this is a very good question, actually. So the reason is, I would say, computational to some extent. So other distances can be used. For instance, KL, you can use it. And from a theoretical point of view, it works much better because it's much tighter somehow in estimating the difference. The problem is that then the value iteration scheme that we use to optimize in the optimistic case, it becomes considerably more difficult. While for an L1, for a total variation distance, we can it turns out to be much easier to, if you want just one single key point to look at, maybe later, is basically this operation here. It's a linear program, so if you have an L1 constraint over P tilde, then it's easy to solve. If you have more complicated constraints, that might be tricky.
Yeah,
that's all.
Yeah. Just a small follow-up question. Would it make sense to like factorize your MDP model into a set of submodels which are strongly interdependent, and then have like a meta So this will reduce the diameter effectively across the different components, and then you would try to solve like you would do something like there's been something called topological value iteration, where basically you factor out the MDP into sub MDPs that have good properties, and then you solve these things locally, and then you have like a top meta solver that tries to actually navigate through these clusters.
Yeah, so topological value iteration is trying to do this sort of decomposition in connected parts. So there have been attempts to do this in a hierarchical clustering kind of approach, to do decomposition of an MDP. Honestly, there is nothing for exploration-exploitation as far as I know, but it's a very, very reasonable idea. The only difficulty is that exploration would actually try to connect these two barely connected components, because it would like to try to go and see what happens on the other side. So it means that you really need to decompose also the exploration part, where you first explore on the strongly connected parts, and then you have a higher level exploration process which tries to understand how to move from one to the other. So it's kind of tricky, and as for today, we don't know how to do that.
Maybe a last very short question with a short answer. Okay, so I do have one. Do you think the dependency C is minimax optimal, or?
So as for the bounds that we have, so let me just, so the lower bound for RL is with D, underscore root. But in so the worst case problem that is used to derive the lower bound is the case where D is equal to C.
Okay.
So we really don't know whether in that lower bound is D or C. And the feeling is that probably it's D.
Okay.
But very rough.
Okay, thanks. Well, thanks again, Alessandro.